So what we'll be covering today is how to find the roots of linear equations. So I will have nonlinear equations. So I will have only one nonlinear equation, and I want to find the roots for this equation. Next set of notes will be if I have a simultaneous nonlinear equations with multiple variables, how I can solve them. So this set of notes will be used only to solve one equation, nonlinear equation, and the next set of equations will be multiple equations with multiple unknowns. Now, as I said before, I'd like to always link the class with practical problems. So I will try to give you some practical electrical engineering problems in this. In the previous set of notes, we concentrated about circuit, because circuit is a very good example about linear circuits. Now here we have to have a nonlinear elements, and we will talk about two nonlinear elements. One of them is the diode. Now I know that this term you start studying electronics, so you might have reached the diode or about to reach the diode. Some of you maybe in the high school have already studied the diode. Okay, so I will give a little bit of introduction. It's not something very difficult to understand, and you will be studying this term anyway. So I thought maybe I will give a little bit of introduction for a good example of nonlinear about the diode, and then I will do the same thing when I talk about sensors. I will use a temperature sensor, which also has a nonlinear relationship, and we will try to solve this to solve some practical problem. So let's start on. So when I have a nonlinear equation, a nonlinear function that have one or has one or multiple zeros, like this one. So this one, for example, has this zero and this zero, and I want to find them. I want to find the intersection. I want to find for f of x equal to 0, what is this point and what is that point. Now, for the purpose of demonstration only, I will draw the functions that will be solving. But in practice, you won't be able to draw them. You won't have access to draw them. So you should be able to solve it without drawing it. But we draw it or have the graph for the function just to see, to visualize the answer as a helping tool, not as a step for the solution. Now, there are two categories of solving these type of questions, and today we will cover the first one. The first one is called bracketing methods. So it is like you are bracketing the answer. So here you will need two initial estimates. So your answer is here, so you have to have two estimates here or two estimates there that are bracketing your answer. And one of the obvious advantages of these methods that they always converge. So yes, you have to know where is your answer lying between, and there are a way to tell if your initial estimates is bracketing the answer or not. Okay, you will see that this is very slow in conversion, but it always converges. And today we will cover the bisection method, and we'll cover only one method. There are some other methods, but we'll cover only the bisection method. And there is something called the open methods. This is, we need only one initial estimate of the solution. We don't need to have multiple estimates of the solution. These ones are relatively faster in converging, but sometimes may not converge. And we will study two methods, the simple one-point iteration and the Newton-Raphson method. So these are the two methods that we will be studying. There are tons of numerical methods in every category, in linear, nonlinear, integration, differentiation. The purpose of this course is not to go through all of them, because that's not practical, but at least touch base of the most important methods and teach you how you can use the numerical method to solve some engineering problems. So we'll start with the bisection method. So here, if I have a function f of x equal to 0, this is what I want to find, and I want to find this 0. And if the estimated limit xl and xu, if I multiply f of x of l, so I evaluate the function at x of l, I evaluate the function, so I will find this. This is your f of x of u, and this is your f of x of l. And obviously you can see here this is positive and this is negative. So if I multiply f of x of l times f of x of u, I will get a number that is less than 0, a negative number. Okay. Now if this happened, it means that you will have at least one root between these two numbers, between the two estimates, between the two limits that you start with solution. If you evaluate the function at these two numbers and you multiply them, at least you will have one number root, or could be more, and they are odd numbers. So here, for example, you have 1, 2, and 3, etc. What will happen if when I multiply these two functions, I will get a positive number? If this is the case, then I might have even number of roots or no roots at all. Because here, for example, if I evaluate the function at f of x of l, f of x of u, both numbers are positive. Even if the function is the other way around, like this, then same thing. So it will be also, and if I use functions here and there, then this will be both negative. So if you multiply, you will get a positive number. Now, if you don't have any root also, you will have this. So if the function is like this, or the function like this, then you will not have an answer. Okay. Now there are certain disadvantages, as the question I received here. What will happen? What is the? Okay, I will answer this for the quiz. Someone asked about what's the limit for the quiz. The limit will be from 8 o'clock to 2:30, so it will be 6 hours and a half. But you have only 75 minutes within this time. What happens if we have a parabola x squared? I will come to this. This will lead us to one of the advantages of this method. I will come to it later on. It says here, what if a function with a single root having multiplicity 2? I don't understand the question. If you can elaborate more. Okay, let's move on. Some of the questions I might answer them as we go, so let's wait until I finish completely the method, and then please you can ask your question. Okay, so what is the steps of the bisection method? So I have a function like this, okay, and I estimated the boundaries, you can say the boundaries where the root is lying between 2 points, okay, and obviously here, if I multiply f of x of l times f of x of u, I will get a number less than 0. Okay, so I know for sure that the answer is between xl and xu. This is the answer. Okay, so what should I do now? Now I need to start the estimate. Where is this root? And where is the best estimate rather than in the middle between these two numbers? So this is the best estimate that you can. So you will find xl plus xu divided by 2. So this is the best estimate that we call it x of m. Okay, so now this is your first estimate of the roots, something in between. Now I have two sections. I have a section from xl until x of m, another section between x of m until x of u. So I have this section and this section. So what should I do now? I will come back and I will do my test again. Now, instead of testing at x of L and x of U, I will test at x of L, x of M, and x of U. And I will do exactly the same test. I will multiply. So I will multiply x of L times x of M. If it is less than 0, if x of L, so it is this function and this is function. Now, it's obvious that x of L times x of M is more than 0, okay? Because both numbers are negative. So I know for sure that the new answer or the new estimate will not be between XL and XM. Now here then for sure it will be between XM and X of U, because X of L and X of U, their functions are less, multiplication of their function is less than 0. So if you have something in between, you have one possibility, three possibilities. Either this number is here, or is here, or is there. It's one of the three. So if it is here, if the number is between these, if the number, actually the number is here, so we know that the new period is between XM and XU. If the number is here, it will be between XM and XL. If the number is exactly here, means you finished your solution. You found the answer. Okay. So let's move on here. So we multiply x of L times x of M. If it is less than 0, then the new limits, the new XL prime will be the XL, stays as it is. So the lower limit of the bracket stay the same, but the upper limit will be now your XM. And now we'll start a new period, which is half the original one. If x of L times x of is more than 0, so I know for sure without even checking that now my lower limit will be XM itself and my upper limit is the XU. So I will take the other half with answer there. But if they are exactly equal to 0, which is most of the time is unlikely, then the root is XM itself and we will stop. So this is basically the answer. What if you have equation with one double root? No, this is not 2 plus 2x. I don't know what this 2 x squared. Yeah, if you have double root, we will come to it. If you have more than one root, we will come to this. You will be able to find every time only one root. You cannot find more than one root. How to choose step 1? This is a very good question. How to choose the limits? Now, in exams, usually I will tell you search the root in this bracket. But let's talk about in practice. You have an equation. How you can find the roots? Now, as an engineer, if this equation stems from an engineering problem, as we will see, then understanding the physics of the problem will give you an idea how to set your limits to find the roots. Okay, and we will have an example about the diode next class. That I have an equation, a very complicated equation, nonlinear equation, and I have no clue where is my answer is. Then by understanding the physics of the problem, we will be able to find this. But for the sake of the quiz, for the sake of the exam, I will give you this limit. So you will working on a certain boundary, especially if the problem has multiple of roots, then it becomes more complicated, because now which root you are looking for, and maybe the bracket now will have between multiple roots. So then you have to have an algorithm that will be able to tell if you are having only one root or multiple roots. But this will leave this for the numerical simulation assignment. Okay, now you find the new estimate, and then you will find the error. Remember, this is something very important. I will see this again and again. This is the stopping criteria, which is the absolute relative approximate error. This is always we will use to know where to stop our algorithm. So you will always compare between the existing answer and the previous answer until you reach to the accuracy you want. If you notice that, and this sometimes happens, sometimes students, they forgot, is it less than 0, more than 0, because they don't visualize the function, so they get a diverging answer, then you will see that your error is increasing, not decreasing. Okay? So once you start to see that the error should decrease every time. This method, for example, we talked about the Gauss-Seidel. I said sometimes it may not converge if it is not diagonally dominant. So if it's not diagonally dominant, it may not converge. But if it is diagonally dominant, it will converge. Okay? But here it always converge. There is no way that doesn't converge, the answer. But sometimes I noticed in previous exams, students sometimes they forgot the criteria. They mix the criteria during the exam. Then they will start seeing the answer is diverging. And this is a way to tell you, oh, you are doing something wrong. That the error now is in every time the error has to decrease, every time. Because you are bisecting this period, you should always coming closer and closer to your answer. But there is an exception. I will come to it later on. So this is the criteria here. So if your relative error is more than what you have been specified, then you go to step 2 and use another upper and the lower guess, and you keep doing this. If you reach this, then you stop the criteria. Let's have an example to demonstrate this. So we'll start with something very simple. We want to find the square root of 11. And we want that until the approximate the absolute relative approximate error is less than 0.5%. So what I want to solve, we find x squared equal to 11. This is what I want. I want to find x. So your function, you have to write this as a function. So f of x is equal to x squared minus 11. So this is the function that you want to solve. So first you have to make this in this format. So you have everything, and this you want to equate this to 0. That's what you want to find. Okay. So we will start the initial guess. Let's say you start with 4 and 5. I mean, this is obvious that you know that the answer is between 3 and 4, but let's start between 4 and 5. Let's see what will happen. Okay, so let's find f at 4. This is equal to 4 squared minus 11, which is equal to 5. Then let's say f of 5. This is equal to 5 squared minus 11, which is equal to 25 minus 11, which is 14. Now, if I multiply f of 4 times f of 5, it is more than 0. If it is more than 0, then definitely the answer is between not 4 and 5. So let's, as we know and we expect this the answer, so let's start between 3 and 4. Now, f of 4, I already know it. I don't need to calculate it. So let me find f of 3, which is equal to 3 squared minus 11, which is 9 minus 11, which is minus 2. So we know that f of 4 times f of 5 is actually less than, it is minus 2 times 5, which is equal to minus 10, is less than 0. So now I know for sure that this is my answer. Okay, so this is the first thing. So I know the limit. Now, a simple question like this, I don't need to give you the limit, because you know that from looking to this, x squared equal to 11. So this is square root of 11. It has to be between 3 and 4. It's very obvious that you can tell that. Okay. Now let's move on. Now what should I do? Then I will find my first answer or first estimate, which is x is equal to 3 plus 4 divided by 2, which is equal to 3.5. Now if I evaluate the function, I already find the function at 3 and I know the function at 4. So if at 3.5 is equal to 1.25 number, is a positive number. So I know that f of 3 times f of 3.5, I know that this is a negative number, so this has to be less than 0. I don't need to recheck the other one because for sure, definitely 100%, the other one is more than 0. Okay? Because you are bisecting, so you are either in the right side or in the wrong side. You cannot be on the both sides at the same time. If it is equal to 0, you are on the answer. This is your answer, which is, as I said, most likely this will not happen. So now you will find that the new answer is between 3 and 3.5. Okay, and if this is the case, now I can go find the next root. So this is, if this is my first iteration, then I will go and find my second iteration, x of 2, which is 3 plus 3.5 divided by 2, which is equal to 3.25. Now this is my second answer, and this is my first answer. Then let me find the error, which is the criteria. Remember, the criteria said I want to stop if the absolute relative error epsilon t is less than 0.5%. So let's see how much is this error here. So epsilon of t is equal to the absolute value of the current answer, the 3.25, minus the previous one, the 3.5, divided by the 3.25 times 100, and you see that this is equal to 7.69%. Still much higher than my limits. Okay, so what I need to do now, I need to find my second. Now, is it between 3 and 3.5, or between 3.25 and 3.5? So now we will find the function at f at 3.25, which is equal to minus 0.4375, a negative number. I know that the function at 3 is a negative number, at 3.5 is a positive number. So I know now the new answer is between 3.25 and 3.5, and then I will find the third iteration, which is the average of these two numbers, and this will give me 3.25 plus 3.5 divided by 2, which is equal to 3.75, and I keep doing this. So here is the answers. This is your x, start with 3.5, 3.25, 3.375, and here is the relative approximate absolute error. Now, of course, for the first answer, there is no answer before that, so there is no calculations. This is my second iteration. I compare the second with the first answer. This is the one that we found, then 3.7, and I keep on. After 6 iterations, I reach the criteria, which is less than 0.5%. And here is the exact answer to, I don't know how many, 1, 2, 3, 4, 5, 6, 7, 8, 9 significant digits. So this is the right answer. Let's have another question, and with this I will end my lecture today. Now here, this is a function. It's a cubic function, so we are expecting that you will have multiple answers. Okay, so if it is x cubed minus 0.165 x squared plus 3.993 times 10 to minus 4. Use the bisection method to conduct 10 iterations. So I will go through 10 iterations to estimate the root of the above equation. Now I will just go to one root. I will not search for all the roots. Then find the absolute relative approximate error at the end of each iteration. So we will find the error at each iteration and the number of significant digits. Now, when we reach to the final answer, I want to see how many significant digits are in my final answer. Now, just for the sake of visualization, to visualize the answer, I will just show you the full drawing of this. So this is how it looks like. So we will have 1, 2, 3 roots. Okay. Now, if I, let's say, select my answer between here, this, let's say, between minus zero point 0.1 and 0.1. This is my the period or the interval I select. So it is between minus zero point 0.1 and 0.2. Okay. So what will happen if I do that? This is positive and this is negative. So we expect there is at least there is one root in between. How many? I don't know. Remember, I don't see this. So now I will start using the bisection method. Okay. Now, let's say I found the average 0.1 minus this is it's 0.05. So you will be here. The next estimate or will be here. So now you will check between this point of. So this is now the new checking point. So this is the previous one. So I just choose something that encompass all the solutions. Then you found the average. Now, when you check between 0.05 to 0.2, you will find that this is a positive, this is positive. So the multiplication is positive. So you have either no zeros or even number of zeros. Okay, we don't know. Okay, but if I select between this and this is negative and this is positive. So I know that at least there is one root. So I will go this way until I converge to this answer. Then I will go this way and start to find, is there no answers at all or there is an answer? So because if you come here, then you will find yourself at certain point at this is the average of it here. Okay, so you will find that there is a root between this and this, and you will keep doing. You will keep doing this. Actually, as a matter of fact, when you are here, you will find that there is a root here and a root there as well. But as I said, for the hand calculations, I will not ask you to do a complete search. Maybe we'll do that in the simulation, because in the simulation it becomes much easier as you can do that yourself. You can program your algorithm to search for the multiple roots until you find all of them. Okay. Now, for the sake of simplicity, as I mentioned, I will look for only one specific root, which is the one that between 0 and 0.11. If you go back here, between 0 and 0.11, something, so we know that we are looking for this root. This is the one, this is the target. Okay, so from the beginning, I will be going through this. And as I said, I will use the graph as a way to visualize the answer so that you can see this clearly. Okay. Okay, good. So I will start with XL0, XU 0.11. Please, you can ask all your questions. Once I am done with the example, I will go and check all your questions. Okay. Now we have XFL, XFU. Okay, and now it's very easy for me to see that yes, there is a root does exist visually, but assume I don't see this graph, so I will find f of x of l, which is f of x of 0, and I will substitute in the previous function, and we'll find that this is equal to 3.993 times 10 to minus 4, which is around the 0.0004. Then I will find f at the x at the upper limit, which is f of 0.11, and you'll find this is a negative number. It's equal to minus 2.662 times 10 to minus 4. So this is a positive number and this is a negative number. So we know that f of x of l times f of x of u is less than 0. Okay, so although it's visually clear here, I know that there is an answer between these two limits. There is at least one root between these two these 2 points. What should we do now? Then we'll find our first iteration, x of m, first iteration. I will add these 2 numbers and find their average, which is 0.00 plus 0.11 divided by 2, which is equal to 0.055. I have now 2 interval from 0 to 0.055. The other interval is from 0.055 and 0.11, and I want to know, is the answer here or there? This is what I don't know. I know f of 0 is a positive number. I know if 0.11 is a negative number, so I want to see what is f of 0.055. Then this will equal, if I substitute, you will find that this is equal to 6.655 times 10 to minus 5. So this is, as we know, is a positive. This is negative. Now this is a positive number, so we know that it has, so this is positive and this is positive. So if you multiply here, you will get it more than 0. So I know that the answer is not here. The answer has to be here between 0.055 and 0.11. Okay, and here is the answer. Now this is now, I start to know that my answer now is between 0.055 and 0.1. So this is now the period of interest. It was this. Now I bisection, so I take the period to half, and now I have this. Now I need to find the new estimate, so the answer will be something in between here, and this is my new period. So I will check. It's obviously, you will see that it has to be in here, and so on and so forth. So here the estimate of the root. Now this is the second root, and as I mentioned, now we are reducing it further. So the answer now is between 0.055 and 0.0825. Okay, so this is now my answer. I will find now in the third iteration. Now I will go and I will find further the answer, and I keep doing this. Now to find the error, now I will have 2 answers. I will have the answers from the previous 0.02. I have this. This is the iteration 2, and from iteration 1, I have the answer which is equal to 0.055. Now it's time to find the error. So to find the error, my error is equal to 0.0825 minus the existing one, 0.055 divided by 0.0825 times 100, which is equal to 33.33%. So this is after the second iteration. Now we need to continue. If you remember the criteria that we asked to stop here, if you go back to the question, what was the criteria here? The criteria, we stop after 10 iterations. We need to stop after 10 iterations. So now we estimate the answer for the third root after that now. So it will be between 0.055 and 0.08. So my third estimate now, x3 will equal to 0.055 plus 0.0825 divided by 2, and this is equal to 0.06875. So this is my new estimate, and then I will keep on checking until we reach to the final answer. So here my absolute error is 20%. It's reduced from 33% to 20%. And here is the the answers. As you can see, if I do 10 iterations, if I want to have less than 5%, then this would be my answer. This is the answer that I'm looking for. If it is less than, because the error is less than 5%. If I want the answer to be less than 0.5%, then this would be my answer, etc. So here I stopped after 10 iterations. Now this is the answer I have, 0.06241. I want to know in this answer how many significant digits. Now you go back to what we have learned. So this is this subject of how many significant digits. You will be using it again and again. So here the criteria, just to remind you, is less than or equal to 0.5 times 10 to 2 minus m, where m is the number of significant digits. So the error that I reach with this answer, this is the error that I have, the percentage error. It is 0.1721%. So 0.1721 is less than or equal 0.5 times 10 to 2 to the minus m. I want to solve for m. Let me divide both sides by 0.5 by 0.5. So this will cancel. So we'll have here 0.3442 less than or equal to 2 to the 2 minus m. Let me take the log of both sides. So this will equal, so your log of 3.442 less than or equal to 2 minus m. So from this, your m will be less than or equal to log 2 minus log of 3.442, or m is less than or equal to m. Sorry. I don't know what's this. Okay. So from this, m is less than this, so your m will be less than or equal to 2.463. Of course, m is an integer, so m should be equal to 2. So you will have 2 significant digits.